All right, this is where the fun really begins. We're going to put the fun in functions, and I want to be very clear at the start of this. This is not the functions of pre-calculus, although it is. So if, you've taken calculus, you've done a lot of math, you've done stuff with functions. This is functions, yes, it's the same functions, yes, but we're generalizing everything. We're connecting functions to what we did before with sets, and we're creating it in such a way that we'll be able to apply it in the future as well. So this is the functions in the more abstract mathematical sense, just like sets were something that kind of is intuitive, but also in the abstract mathematical sense that we can use for other things. So let's start off with an example before we get into any definitions. Now, let's say my screen worked and that we're looking at two sets. And let's say this first set, let's say that's the natural numbers, 1, 2, 3, 4, etc. And the second set is all the integers. Now, we can talk about a relationship between elements in these two sets. Let's start by talking about a relationship that you might have heard about called equality. Okay. Well, then there's an element in this set called the number 1. That element is also over here. So 1 has a relation with 1, right? And so on, right? 2 could be this little dot. This little dot's also here as well. We got this. So everything in N has a relationship with something in Z, right? We keep on going and going. But remember, there are also things in Z, that aren't related to anything in N. Okay. So this is one kind of relation that we can have. You could have another relation. Again, let's also look at N, and let's have another relation called Z. And let's look at the greater than sign. So let's look at the number 5, for example. What elements in Z is 5 related to if the relation that we're talking about is the greater than sign? Well, 5 is bigger than 4, it's bigger than 3, it's bigger than 2, it's bigger than 1, it's bigger than 0, it's bigger than -1. 5 is related, just putting little dots to show these things. 5 is related to all of these things. 5 is related to infinitely many things here, if the relation that we're talking about is the greater than sign. So of course, we'll eventually start talking about functions, and you're probably going to be able to say, okay, I see this thing over here, equality, is a function. This thing over here, greater than sign, this is not a function. All right. And that's one of the things that we're going to talk about. I don't know what is going on with my screen, but hopefully it clears up so you guys can see things a little bit better. All right. Yeah, and eventually we'll talk about topics such as surjections, bijections, domain. You may have heard that word before, and just talk about how they apply to here. Okay. So again, over here, we could say that an element A is related to B. We could also write A equals B. For example, 2 equals 2. We could also write 2 is related to 2. So these are all valid things that we can say here. This is a notation that we'll be using. And of course, we could say, maybe A is not related to C. We could say 2 is not equal to 3, for example. All right. And so this is some of the notation that we're going to be using with this R for relation. All right. And now I have a question for you. And my question is, if A is related to B, is B related to A? And certainly, in the terms of equality, the answer is yes. If A equals B, B equals A. That's a reflexive property. But it's not true for all relations, right? Because if we look over at this relation, 5 is greater than 4, but 4 is certainly not greater than 5. So we'll say 5 is related to 4, but 4 is not related to 5, with our relation being the greater than sign. So these are all just a little preview of things to come, right, which is pretty fun. And again, we're going to get into some more abstract stuff in the future sections. But just an introduction, a connection to what you've seen before in a math class. So let's start with a more abstract definition, which lets us start talking and connecting to sets, which is pretty exciting, right? So a relation from a set A to a set B, that relation is a subset of A cross B. So there is so much. Let's not even keep reading. Let's stop right here. There's so much going on from chapter 2, from our section about sets already. A relation is a subset of the Cartesian product. Remember, the Cartesian product of two sets was a bunch of ordered pairs. Every possible ordered pair of A comma B, where A comes from set A, B comes from set B. So a relation is just a subset of all of those. A relationship is a collection of ordered pairs. And that's the second half right here. So specifically, if we look at the second half of this definition, a relation is a set of all ordered pairs where the first coordinate comes from A, the second coordinate comes from B, and then we say that A is related to B, if that's the case. All right, so let us look at an example here. So let's say A is the natural numbers from 1 to 6. And let's say B is the natural numbers from 1 to 4. And let's define a relationship. Let's use lowercase a and say A is related to B. Or again, we could also say, right, the ordered pair A comma B is in the relation. Remember, the relation is a subset, which means the relation is a set and can have elements. So A is related to B if and only if, that's what IFF means, if and only if, A minus B mod 3 is equal to 0. So remember, the modulus operator is just remainder. So let's look at some examples, right? So let's pick any two elements of A and B. I don't know, is 1, 3, are they related to each other? Is this in the relationship? Well, let's check. What is A minus B mod 3? Well, that's 1 minus 3, that's negative 2 mod 3. So is negative 2 divisible by 3? The answer is no. If you try to divide it, it's been a while since I've done modulo with negative numbers. But it certainly wouldn't be 0. Would it be, I think it'd be 1. Okay. So I'm just going to write, I don't want to have this wrong in the video. But yeah, it's not 0. It's either 1 or 2. I think it's 1. But there we go. Either way, we'll conclude that 1 comma 3 is not in R. 1 is not related to 3. Okay. Well, what is R here? Let's take this a step further. Can you write all the things that are in R? Try it. Try to pause the video, brush up some of your math skills, and let's see if we get the same R. I'm not sure I'll go through everything, but I'll give you at least some elements of R. Pause the video and give it a try. So we need A minus B to be divisible by 3. So let's just start with 1. 1 minus 1 is divisible by 3. Yep, 0 is divisible by 3 with no remainder. And then 1 comma 4 is as well. No other pairing goes with 1. And then you can continue going on, right? 2 minus 1, nope, 2 minus 2, yep. And then 2 minus 5 would be as well, but 5's not in B. So 3, oh dear, we might have a problem here. Yeah, 3 minus 3 is, but there's no other elements for 3. And then we can go on. It's going to be 4 and 1, 4 and 4. It's going to be 5 and 2. And that's it. And then 6 and 3. And that's it. And I believe I've got them all. If I don't, let me know. I'll give you an extra credit point or something. But yeah, that's pretty much it. That's a list of all the things that are related to each other with this definition. Let me know if you have any questions about that. We're going to do another example. So let's say that this one will be a little easier, I think. Let's say X is the set of some colors, blue, red, and yellow. No, let's add another color. Let's say, let's see, not purple, not green, not orange. Wait, how many letters is orange? O-R-A-N-G-E, 6. All right, let's add orange. Why not? And purple. Okay. And let's say Y is the set of natural numbers. 1, 2, 3, 4, etc. Okay. Let's say that X and Y are related. We're going to call this relation S. Here, S is the relation. X and Y are related if and only if the number of letters in little x is Y. So what I want you to do is I want you, again, to pause the video and write down the relation here. What is S? Two elements are related if the number of letters in X is in Y. And interesting comment here. Earlier, I asked you the question, is this the case? If A is related to B, is B related to A? And I said it's not always the case. And we saw that it was true for the equal sign. It was not true for the greater than sign. What's interesting here is that this question doesn't even make sense for this example due to the relation. You would have to create a different relation to go the other way because A and B are different kinds of sets here. The input and the output are different kinds of sets. They have different elements and kinds of elements in them. Anyway, so S, what was it? Hopefully you found it. S is going to be the set blue and all the outputs for blue. Well, blue will always just have 4 letters in it. We have red. That just has 3 letters. We have yellow. That is 6. We have orange. That is 6. And we have purple, which have 6. Lots of 6s here. Interesting. All right. So that's our relation. And it's okay that they all have 6s. We'll talk more about that when we get to bijections. But that's the idea, and that's this video. Let me know if you have any questions, and welcome to functions. I'm excited to be here. Some of the stuff we teach in this chapter is really cool, and I haven't been able to teach it for a really long time, so I'm looking forward to it. Hope you are too. Have a good one.